the hardest part of this course is here. Okay? Last few weeks, okay, they are all about concepts. Last few weeks are all about knowledge. This time is not about knowledge. You have to think together with me. I tell you there is a bug, you have to think together with me where is the bug. I tell you you cannot interchange two lines of code. You have to think together with me why you cannot interchange them. Okay? So this will be the hardest part of this course. And the time is not good, midterm period, right? Okay. So I talk about the semaphore. And I tell you that the semaphore is everywhere. We will use Semaphore to establish some kind of protocol between two processes. And the protocol, of course, is in terms of a program. Okay? So 3 types of program. One type is producer-consumer. Okay? Networking, like you want to send something to, you are staying between two neighbors. Okay? You are transferring data from the left-hand side to the right-hand side. So the body itself is a video, and also you are a buffer. Maybe you cannot handle too many packages, you cannot handle too many messages passed from your left. Okay, so you are bounded. And in networking or also non-networking stuff, here is non-networking stuff, how to handle those bounded buffer is a challenge. Okay, but the implementation of bound buffer is not a challenge. Okay, you have already learned it. You have already learned it in data structure. Still remember ring buffer? How many of you still remember what is ring buffer? Ring buffer. Stanley, do you know? Oh, you don't know. You only know this phone. Ring buffer, bound buffer. Ever heard of it? How can I describe ring buffer? Yeah, okay. Forget about ring buffer. Okay, linkless. Okay, linkless implementation of a queue. No, right? You should know it. Ring buffer, yeah, some people know what is ring buffer. Okay? So basically you can imagine that this is a array, okay? An array, and you implement queue in an array. Okay? So this is a bound buffer problem, and there is a producer, and also a consumer. One is producing items or bytes, one is consuming the bytes. Okay, so this is the illustration. Shouldn't have any problem because I have already talked about it in the beginning of this part. Right? The left-hand side will do something, and you hope that it is in an FIFO manner, first in, first out, right? First in, first out manner, so it is a queue. And this is a shared queue. Okay, this is a shared queue. Both processes, okay, we hope that they will run in parallel. Let's say we have a multiple CPU or a CPU with multiple cores, then they will run in parallel. Now, if there's one in parallel, we will have race condition, right? So what are the things that you have to protect? If it's a queue data structure, the array itself, right? Also, the head pointer, the tail pointer, okay, you have to protect all of them. So whenever you try to access to the length of the queue, you need to protect it. Whenever you want to enqueue, you have to protect it. Whenever you want to dequeue, you have to protect it. And protection is very simple, just mutual exclusion, right? When this guy tries to write things, I don't allow the liars, the consumer, to pick up anything. It seems to be as simple as that, right? If this buffer is infinite, of infinite space. If it's of infinite space, then it's a simple mutual exclusion problem. Why I say that this is in infinite space, there's no problem. Because whenever you try to write things in, you will always access. You will always access. You will never fail. When you will fail, still remember, if you try, the LS try to write things, you will fail if and only, one side. If this buffer is full. So if it has infinite storage, okay, it is a simple mutual exclusion problem. If it is not, okay, this is a finite space there. I only contain a 4K bytes, let's say, 4K bytes. Then after 4,096 bytes written in there, How about 4097 bytes you cannot write in? So this is no longer a very simple problem. To illustrate a bit, I prepare this is for your revision. Okay, I already talked about the story. Okay, I already have an animation to assist you to understand what is the problem about the case that it is a bound buffer or a finite space buffer. Now I make this example very outrageous. How outrageous it is! The usable space of this queue, of this FIFO buffer, only 1 byte usable. Okay, you can only enqueue 1 byte, and it will change from empty immediately to full. And when you dequeue it, it will immediately change from full to empty. Okay, so that I can write a shorter example here. Now the example starts with this guy is running, this guy is waiting. I don't want them to run in parallel because I don't want to complicate the story. If you want to have them running in parallel, okay, just set up a mutual exclusion requirement. Okay. Now, since they don't run in parallel, I can just put aside the mutual exclusion problem. Let's say this guy uses a write system call to write to the bound buffer. Okay. As it only have one byte space, okay, I don't need to care about FIFO property. Okay, 1 byte. Can you have 1 byte but not FIFO? No. Okay, so I don't need to care about FIFO property, and this write will have 2 consequences: either successful or because of its full, it's failed. Now it is the beginning of a story. So when I write to it, it was successful, return success, and you can go on. But some status change inside the pipe data structure. You only support 1 byte. Say the example is support 1 byte. So I already saw it here. And write system call gives you 1 byte. Good. I can successfully write it, but it's become full now. Shouldn't have any problem, right? I just have 1 space loss. Then I'm the LS. I will continue to write data, right? Because if I type LS will produce a stream of data, right? So the next byte is coming. The next byte is coming. Now the next byte meets the problem. What is the problem? The pipe is full. Okay? If the pipe is full, the write system call return an error. If that's the case, then the LS program should handle it. But you know, LS program don't know about you have a pipe. So the implementation of the operating system will do something like this. Okay? This is a part of the operating system that you call write system call, and I find your target is a pipe. Also, yeah, one more condition. I know you are a pipe, and the pipe is full. So this is all handled inside the kernel layer. Then I will put your call, the write call, into a block state. I don't return. Yeah, very interesting. Why don't return? Okay, so when you look at the LS, the program suddenly stopped. I finished writing the first byte. I tried to write the second byte. It stopped there because it's full. So it's under the kernel control. And what is waiting for? It's waiting the helper, your partner, the consumer. Now the consumer comes. Okay, the consumer suddenly try to get something. First of all, it will call the system call read, try to read 1 byte out. And it was a success because originally there is a byte of data inside the pipe. So I'll pull it out. Pull it out. Let's say in this green area, I just print out to the screen, okay, for that byte. Now I'm not satisfied with 1 byte. Okay, I will continue to read the next byte, but I already heard about that this pipe limit is 1. So the limit of the storage is 1, so you don't have a second byte. So with this, I will block the read call as if I'm waiting for the keyboard input, right? I call get char. I call get char, but there is no input, so the get char stand there. Okay, it's still the same here. You try to read something, but no data, so it's just stand there without any useful progress. Okay, so again, here it will under the block state. Now, how about this guy? When this guy will be unfreeze, okay, it will be like this. this gray area, I just draw up to here. Because if the pipes change from a full status to a non-full status, okay, then that means that someone has already taken out some bytes. So it is good for you, good for this guy, to be unblocked. So here, I already stated that this guy is unblocked, but because I want to make this example easier to understand, I only allow one process to run together. Okay, so there's a dot here. It is ready, not running. Now context switching comes, and the story is continued that, okay, I can write that pending byte. So where is the pending byte? The pending byte comes from here. It comes from here. So originally I want to write one byte, and I'm forced to be waiting for some time, and because of context switching, I can resume executing. So that byte immediately write to the pipe, and the pipes change from here. I consume one byte, so free up one slot, and then here this guy put back one byte, consume that slot, put back the one byte into that slot. Is it clear? Is it clear? Any problem? If there is no problem, so I guess you can extend example to a multiple bytes space. Okay? So I didn't explain how kernel support this kind of blocking or non-blocking, or maybe some denials. Okay? But I can tell you that this is implemented using Semaphore. Okay? Now, what I'm going to do next, you already know that, okay, the pipe itself is fantastic. Yeah, kernel support. No need for any coding of Semaphore that you need to write. Okay. Now what's next? Next is, pipe. Who didn't call pipe? Okay, that means that who didn't start doing phase 2. Yeah, if you have started doing phase 2, you have called pipe, right? How to call pipe? You need to, before the fork, okay, you call pipe. And when you call pipe, then you call fork, so that two processes can look at the same pipe, right? Now, I want to emphasize this phrase. The phrase is, two processes share one pipe. Okay? So how about I have a crazy requirement. My crazy requirement is, I want multiple producer versus multiple consumer. Yeah, why not? In your application of the assignment 1, the shell, we only support one producer matched to one consumer. Okay? Because it's nonsense to have multiple producer and multiple consumer. But how about other environment, like networking? Okay? And networking, I have a multiple data source. Okay? Want to send to the network card. The network card contains a buffer. Yeah. If you don't understand, okay, there is a hardware, okay, called network card, okay, and there is a hardware buffer inside that hardware, okay. So you have multiple sources, okay. I don't know how many processes you have. Your BT, you have your QQ, you have your no more. Okay, Skype, what else? LOL, okay. Yeah, a bunch of data try to access to the network card, and they all try to write. Yeah, so multiple producer and one consumer, the hardware itself. Okay? So another way is also doable. Okay? I have a network card. Yeah, consuming data from the network and try to distribute to different processes. Different processes have different requirements, but they will access the card at the same time. Okay? So how can I support this? How can I support this? You need special code. Okay, and the special code is no longer easy to read. This is the code. I copied it from the book. And I really try to implement it, although I implemented using threading. Now this is called processes. Threading, later on we'll talk about it. Okay, this is a processes. Now, let's talk about some of the assumption, or use your imagination to think about it. The assumption is number 1. This process, okay, called producer process, will only execute this function. Say this is the case. It's only execute this function because it's while true loop, so it won't go out. Yeah, assume it's like that. And the consumer also do the same thing. Okay, it contains a while true loop or while loop, and remember that they won't stay away. Okay, they won't suddenly I don't know where we have a return. Okay, and suddenly return from the functions. This is number one assumption. Number two assumption is you cannot see the pipe, right? So where is the pipe? The pipe is here. Okay, the pipe is here. And I don't show the buffer. I don't show the data structure of the pipe. You imagine that there exists a pipe. So that's why I said that you need to use your imagination. Assume you understand what is a pipe. You understand, if you don't understand what is a pipe, understand what is a queue using array implementation. So you have an array, you have an integer for head, you have an integer for tail, and they put together becoming as data structures, components. It doesn't show here. And why I say that this is the pipe, or this is the buffer. Let's read it. I first define a constant called 100. So I assume that the finite buffer only have 100 slots. Okay, so this is the assumption. There is a bound buffer. Okay, I sometimes use a term called bound buffer, and the size is 100. It will only have 100 slots. Okay, and of course I have to define what is semaphore. So just like previous case, I will define this as a semaphore. Now remember that because semaphore is shared. It's shared. Okay, and if you remember previous mutual exclusion implementation case, we should never touch its value. We should never inspect its value, because once you inspect it, other processes may have a chance to update it and you get the wrong results. So in these two codes, now this is the third assumption, or I would say this requirement. You cannot see any statement here, I check the value of any semaphore. No, I never check it. Okay, remember, I never check any semaphore value. Okay, what else? What else? I have initialization values to those semaphores, and it's no longer binary semaphore. Now, previous lecture I talked about one case for binary semaphore, either 1 or 0. 1, if I treat the semaphore as Deadlock, 1 means open. Okay, it's open, and I call down to cause this 1 become 0, it means block. If it is 0, you try to block, lock it again, so you will get blocked there. Okay? So it's binary semaphore 1, 0, 1, 0, 1, 0. Now you can see different semaphore and 0. Okay? 1 is called empty, 1 is called full. I will explain it, don't worry. Okay? So I will make sure that every people after this, we still have 25 minutes, so you should have enough time to understand it. One more, this we remove item and insert item. You don't need to care about its implementation. Just treat this as the critical section. Now together we read this code. What is the producer function? Producer function as if it is a simple mutual exclusion case. Simple mutual exclusion case. We have an entry in red color. We have the mutual exclusion. The mutual exclusion setup. Then I will execute the critical section, the critical code, to insert it to access a bound buffer. What's next is to unlock it. So there's lock, access, and update, and then unlock. Here is also lock, access, and update, the queue, and unlock. Okay? And this will go indefinitely. Now, what are the problems? The problems is why the lock and unlock is so complex. Yeah, it contains more than one statement, double down, double up. And they work on different semaphores. And they contain some meaning there. Okay? So I give you some questions now. The question is, there are two, basically it's a flow of this lecture. The flow is I will tackle question number 1. I guess I can only tackle number 1 in this lecture. What are the use of these three guys? Can I remove any one of them? Okay? So, let's go back to one page earlier. You need to discuss with your neighbor. Now, imagine I remove all the down and up call concerning empty and full. Okay, all the down and up call concerning empty and full. So remove it in your mind. Remove them here. Also remove them in your mind. Is it equivalent to simple mutual exclusion control? Look at the initialization value of mutex. Mutex is 1 in the beginning. Okay. So both processes try to call down mutex. Who win? Who win? Only one guy win. We don't know who win. Okay? So make sure that you understand, oh, only one guy win. And when this guy win, because it's disabled the interrupt while inside the down call, so that's why only one guy win. And while one guy win in that case, only one process can change the mutex value from 1 to 0. So only one guy can lock. Okay? Now I said that you should remove in your mind this line, this down empty. You only have the down mutex, and here remove the down full, only have down mutex. Okay, oh, this is pronounced as mutex, M-U-T-E-X mutex. And why we have this word? This word is a short form of mutual exclusion. Okay, it's mutual M-U-T exclusion. So put it together, we call it mutex. Okay, don't call it mutex. It's mutex. Is it equivalent to a simple mutual exclusion control? Yes, right? Remember what is simple mutual exclusion control? Don't remember, huh? So the simple mutual exclusion control is here. It's here. Yeah, page 56. The simple mutual exclusion control say that I want to access a piece of code in a mutual exclusion manner, so you will have a down semaphore, and I don't know what it says. Oh, it's supposed to be starting with the value 1. Okay, S, start with value 1. So I will down it from 1 to 0, and after using it, I will up it, change it from 0 to 1. Okay? So this is a simple mutual exclusion use case. Back to here, if I remove all the call concerning full and empty, they are just the same as simple mutual exclusion in this case. Okay? So I already told you why we have mutual exclusion and why it is initialized as 1. Because we want to set up mutual exclusion. Okay? We want to set up mutual exclusion to protect the buffer. To protect buffer. Now, this is the reason why we have the mutex. You cannot remove it. You cannot. Now, how about the full and the empty? They have different initialization value, which is not 1. So it seems that it's not for mutual exclusion. I can tell you that it is for the blocking control. So what is the meaning of the blocking control? Okay. So I have already talked about this. So I color them. They form a pair. They form a pair. Now, use your imagination now. Don't look at the consumer code. You only look at the producer. And imagine that in an environment, we only have one producer. And that producer keep running. Because it's while 1, while true loop. Okay? Tell me when it will stop. It will stop. But when? Loop for how many times? Yeah, the hint is the line I color in red. I give you 1 minute. Don't look at consumer, okay? I see some eyes over here. No, don't look at here. Look at here. Okay? Yeah, to prevent you look at there. Okay? Look at here. Oh yeah, then I fail. You need the initialization value. Okay, forget about this. You need the initialization value, okay? The initialization value of empty is n. Now tell me for how many loops it will stop running. Or why it stop running. If it will stop, why? Oh. Yeah, you need to understand this. I usually set up quite a lot of marks concerning this part in final exam. Okay, hands up. Will it stop? So think that it will stop. Only one? Oh no. Or two, three. You don't know. Okay, how about inside? Will it stop? Will it stop? Or you have stopped down? If your brain has stopped already. Okay, so how many times it will loop for? N, no, n plus 1. Because you need the last time. you need to look for a start from n, right? N minus 1, minus 2, minus 3, and down to 0. So there's n minus 1 times. Sorry. N minus time. Okay. Now, why is stop? Okay, I ask you another one. End up, why stop? Okay, you raise up your hand. Because which line? 6. Empty becomes 0. Okay. And then it will stop. Right. So we have some fragments of answer, but those fragments cannot make it into a big story. Okay. So I will tell you what the story behind it. The story is not difficult. Let's say we only have this side. Don't consider consumer. We have only the producer, and producer start with empty value with n. Now I will execute it first for the first time. Let's say n is 100. Okay, it's already defined here. So n is 100, then it will decrement into 99, 98, all the way down to 0. Right? You keep spinning here. You don't need to consider the full yet. Okay? You only consider line 6 first. It keep on decremented, and from 100 down to 0, and when 0 has ended up, okay, sorry, it's end up recording. Okay, Matthew, right? Yeah, talk about it. Line 6, tell me, give me a 0, right? So this 0 means what? If I keep on down, the semaphore definition said that if it's 0, I will block there. I need someone to help me to wake me up. This is the control. Now, this is only telling me one thing, that I can only down for 100 times. So why 100 times? Or 100 0. 100 plus 1, I mean. 100 plus 1, because the last time is the one that's called me block. Okay? So for the previous 100 times, it means you have 100 slots of that bound buffer, because you can insert it for 100 times. You can call this insert for 100 times. Down once is get past. From 100 to 99, you insert one item. From 99 to 98, insert another one. Down to from 1 to 0, you insert the 100th items. Then what? You cannot put in 101, because 101, you look back there, find that the empty is 0, block there. Okay? So that means what? That means this semaphore is not simple, not naive, very complicated. It means the number of slots that contain, this is an empty slot basically. This means it's empty slot, 100 is empty slot for you to insert item and keep counting the number of empty slots there. If you use up, I will cause the producer, okay, to go to sleep, block for some time until this guy rescue him. Yeah, I introduced this guy. His name is called consumer. Okay, so the consumer start. Let's say this guy go to sleep. Consumer start. Now, how can this guy rescue the block producer? It's the pair of red line. Pair of red line. Now, remember this guy. What is this guy's status? I don't know whether you have do the revision or not. I hope not. I hope. I believe not. Okay. Okay. So when you call down, and it is already 0 now, there's S value is 0. I go to a block state, but together, my PID is a waiting list of that particular semaphore. So when there's a partner call up over this semaphore, and change it from 0 to 1. Now the trigger is 0 to 1. The trigger is 0 to 1. Then I will be unblocked, I will be free, okay? And then the 1, 2, 3, 4, as well as more processes will be stop executing, and depends on how the scheduler pick me. Now remember this. Oops. Okay, so look back the red guys. The red lines, the pair of red lines essentially is a pair. Okay, so what does that guy do? I don't care for how many times. I just imagine that there is this guy's only a get birth. Okay, I just create it. And so happen this guy is blocked. Now when this guy goes down this code, the first block, the first hurdle is just down full. Yeah, if the full semaphore is 0, then we will doom, okay? If it's 0, then this guy is blocked, bye-bye. Yeah, you have to reboot the computer. Okay? Now, will the full value is 0? No. So someone already said no. Then what is the value? No, do you know? No, you already lost. What is the starting value of full? Starting is 1 and not. By that time it's 100. Okay, so starting with 0, the full, and why it's not full that our classmate already said that no, it's 100. Why? Because here. Because of here. The producer, once it's insert one item, together it will consume the empty semaphore down by 1, but at the same time, it increments the full semaphore from 0 to 1. Now, whether the 0 to 1 will rescue anyone, we don't know. Okay, because my previous story is like this, only have the producer. So from 0 to 1, the full from 0 to 1, we don't know who will be rescued. Say no one will be rescued. Go ahead, then we will decrement this by 1 and together increment this by also 1. So when this guy is blocked, and this guy start executing, the consumer will carry full equal to 100. So this is not a hurdle, this is not blocking. Okay, I can go down. And how about the mutex? It is 0 or 1? 1. Okay, although we have changes a lot, but look at here. The mutex is in a pair. Down and then up, down and then up. Down and then up. So 1 change to 0, which is down, and then up 0 to 1. 1 0 0 to 1 1 to 0 0. Okay, but so happen that it get blocked by this line 6. So mutex is 1. So I can get past the second hurdle. The 2 hurdles don't stop me. Then I will consume the item produced by the producer. And what's next? Of course, I will unblock the mutex semaphore, because the mutex semaphore is to protect the bound buffer only. Together, I up the empty. Now I tell you what is empty. I already tell you what is empty. Empty means number of empty slots. So it means number of empty slots change from 0 to 1. And this is the trigger. From 0 to 1, this guy will zoom. Why? You do remember just now, I showed you back the slides, that when the trigger is changing a semaphore value from 0 to 1, the processes in the waiting list will be unblocked. So the process will be unblocked right at this moment. Yeah, this is the mechanism. Okay, how they communicate is by setting up a pair of semaphore. Okay, so when this guy will be blocked again, if say this guy after it is unfreeze, I don't know why it won't pick it. The scheduler won't pick this process. The scheduler keep on picking this process. So will this process block? If yes, when? Yeah.
When he has consumed all the remaining items in the code.
Yes, he already gave me the physical meaning, not reading the codes. Very good. The physical meaning means the real mechanism. The real mechanism is, I just copy his word. He said that when the consumer consumes the remaining items, consume them all, then this guy will block. Using code, what is the meaning? The meaning is this down full, basically, I shouldn't call it full. Maybe I call it items or number of items. It basically means this semaphore, the value itself, documents how many items in the buffer. Right. The full actually documents how many items. So when I download, it means that I'm prepared to consume one guy. Okay, I'm prepared to consume it, and then I really consume it. But by the way, I make a free slots again. So I up one free slots. Yes? Again. So, oh yes, I have another execution order. How about this guy one first? Right. Yeah, later I will talk about it. Okay? So, any problem with this execution order? This guy keep on running, and then block. And why this block is because it's consumed all the empty slots. Okay? So this is the physical meaning. I consume all the empty slots. And then, I don't know why this guy suddenly start. This guy start will produce a value to this empty because I change it from 0 to 1 and unblock this guy. But when the scheduler pick this guy is another story. Okay? So let's say I will keep on letting the consumer goes, and suddenly it will block because it says calling down too much, too many times. How many times you can call? For 101 times, then it will block. Because you already consume all the values produced here. So just like cooperation, right? They cooperate. When you consume one item, you have a chance to produce one item back by adding the semaphore values. Any questions? Any questions concerning this execution order?
So we are not assuming any context switching during this.
No problem. You can have context switching anywhere.
So if we have context switching, so the consumer may begin to consume the data when the queue is not full.
Yeah, no problem. You can. It is allowed. It's allowed. Context switching can happen at any time, any place. No problem. Yeah, sure. Yeah. Yes. Basically, the average case is that this guy block, okay, is very rare, very rare. Okay, assume that these two guys have the same priority. They consume the same amount of CPU resource. Assume that. Then this guy run for some time, then this guy run for some time, and then context switch back. Producer run for some time, and then consumer. So basically, it won't. A fair way that you will produce up to the limit and then block. Okay? So the blocking, unless you have too few slots or your item is too big. Okay? Very rare. Now, she has asked another question. So what if this guy execute first? I change the entire story. Consumer execute first. What will happen? Yeah, no problem. No problem. And what is the scenario? Yeah, the full is 0. Immediately, when this consumer try to consume from an empty type, The pipe is empty. You want to consume from an empty pipe block. And let's wait for the producer to rescue him. And when producer execute, it will eventually up full, so that it rescue this guy. Wow. Is this too much? I mean, if you ask you to write this code from scratch, you will die. But if you trace the code, you can trace the code. That is very good. Okay? Any problem? This is not the only code. We have two more. This is not the only one. We have two more. This is the classical problem solution. We have two more classical problems, remember? Now, before you go back home, I want you to think of one problem. You can look ahead a few slides. The problem is, okay, so this is the conclusion. I finished talking about these slides, actually. Now, go home, think about it, okay? You need to think. If you don't think about it, okay, please make sure that in the examination don't write anything, okay? I don't know, I don't want to guess what you're about. If you don't know and you don't understand this, so that's why I guess that this set of things need to make up pass. The problem that you go home to think about it is, what happened if I interchange these two codes? Yeah, this is not the original version. The original version is empty. 96 is empty. Is 96? Yes. 97 is mutab. Empty, then mutab. What if, by accident, I interchange that? Will it cause any trouble? Yes. Yeah, if you look ahead, then you will know, yes, big trouble. Okay? It is a big trouble. Okay? So make sure that you go home, try to revise this part. Okay? Yeah, this is just like learning swimming. Okay? The first time you jump into water, it's cold, freezing, and you need to get drunk. Okay? So this is the drowning time, and you need some practice. You need to read more. Okay? And to understand how to design such kind of thing. Okay? That's it? We will meet again in Thursday. And in Thursday, we will have a tutorial. Later I will post up the announcement. The tutorial is not teaching anything. The tutorial is, student will be there. Okay? And you ask him questions. I know that you may have many questions. Okay? I will pick one or two tutorials to attend also. Okay? To help out the TA to answer questions. Okay? See you on Thursday.